Hi, I'm Divjot Singh from VIT University, and I'm going to explain you this example.
Hi, I'm Tushar from VIT University and I'll be explaining you this question.
I'm here to explain you about three address codes and the concept of quadruples and triples. So, in three address codes, there is at most one operator on the right side of an instruction. That means that is no built-up arithmetic expressions are permitted. Thus, a source language expression like x plus y plus z x plus y star z might be translated into the sequence of three address instructions like t1 equal to y star z and t2 equal to x plus t1. Three address codes are built up from the concepts of addresses and instructions. In object-oriented terms, these concepts correspond to classes, and the various kinds of addresses and instructions correspond to appropriate subclasses. Alternatively, three address codes can be implemented using records with fields for the addresses, records called quadruples and triples. So here we take the example a plus b star a plus b minus a plus b star d. So we'll take a temporary variable t1 which would be a plus b, and another temporary variable would be t2 which would be t1 star t1. So now our t3 would be to generate a plus b star d, which would be t1 star d. And now to generate the whole expression would be t4 equal to t2 minus t3. So now to generate the quadruple table, we will create a four column table. Uh, the columns would be first column would be operator, second column would be argument 1, third column would be argument 2, and fourth column would be result. So for the first expression, uh, we would write our operator as plus. Our first argument would be a, second argument would be b, and the result would be t1. So the next would be operator would be star. First argument would be t1, second argument would also be t1, and our result would be t2. Next would be um, our operator would be star, t1, d, and result would be t3. Then operator would be minus, t2, t3, and t4. So we have now created the quadruple table. So for the triple table, I'm going to tell you a little about triples. A triple has only three fields, which we call operator, argument 1, and argument 2. Using triples, we refer to the result of an operation x of y by its position, rather than by an explicit temporary name. Before building the triple table, we would construct a syntax tree for the expressions. So we have a plus b star a plus b minus a plus b star d. So we would firstly construct a plus b, which would be like this. Secondly, we would construct a plus b star a plus b. So we would construct another a plus b and combine them with a star. So next we would try to construct a plus b star d. So we would construct first a plus b and combine it with a d, and then we would join both the expressions with a minus. So now we have the syntax tree for the expression. For the triple, actually a triple has only three fields, which would be operator, argument 1 and argument 2. Using triples, we refer to the result of an operation x of y by its position, rather than by an explicit temporary name. So it constructs a table for representing the triple. First column would be operator, second would be argument 1, and third would be argument 2. So now we would like to generate a plus b. So operator would be plus, argument 1 would be a, argument 2 would be b. So we would now construct a plus b star a plus b. So the operator would be star, and argument 1 would be 0, and argument 2 would also be 0. Then we would construct a plus b star d. So operator would be star, argument 1 would be 0, and argument 2 would be d. And now for the final expression, operator would be minus, argument 1 would be 1, and argument 2 would be 2. So now we have the expression a plus b star a plus b minus a plus b star d. Thank you.
Now let's take a look at this problem. It says prove LR0 is equal to SLR1. Using the example, S gives B, A, C, B, C and D. Now the first thing we want to know about these parsing techniques is that they are both very similar. They are both bottom-up parsers of the category LR. The only difference is in this one, which tells us about the look ahead. We'll cover this later. Let us have a quick look at the structure. They both have parser here, and access to stack here, input buffer, and a parsing table. Now all the difference between LR0 parser and SLR1 parser comes in the parsing table. Rest everything is similar. Now the first step at building the automata is numbering the productions. Our productions were S gives B, A, C, S gives B, C, and S gives D. Let's call this production 1, production 2 and production 3. The next step is augmenting the grammar, which means introducing another non-terminal S dash, which is complement of S, and adding a production S dash gives S to the grammar. So now we're left with S dash gives S gives B, A, C, S gives B, C, and S gives D. Let's call this 0, 1, 2 and 3. Now the next step is called closure. Now for understanding closure, let's introduce a concept called items. Now how do LR parsers know when to shift and when to reduce? An LR parser makes shift reduce decisions by maintaining states to keep track of where we are in a parse. These states are called items. Consider a production A gives X, Y and Z. Now this production can have four states. A gives dot xyz, A gives x dot yz, A gives x y dot z, and A gives x y z dot. The dot is the operator which tells me about where I am in the parse. Now let us consider A gives x dot y dash. A gives x dot y dash indicates that we have just found a string derivable from x in the input, but we still need to consider x, y and z. Now consider A gives x, y, z dot. We have seen the body xyz and now it is safe to reduce xyz to A, is what this production means. And also for productions like A gives alpha dot B gamma. Now keep in mind, whenever I am considering this, I also need to consider all the productions of B, since the dot is before B. Now let's make the automata considering the first production. S dash gives dot S. Now the dot comes before a non-terminal, so I need to write down all the productions of S, which goes S gives B AC, S gives BC, and S gives D. Now we will call this set of items as I0. And now we will see the transitions from this I0 item. On S, we go to S dash gives S dot. Since this is the final state, because we have seen the body of S and I am done with all these steps, so I'll write it as I1. Now if I make a move of B, I'll land S gives B dot AC. Now I don't have productions for A, so I'll write it out as it is. So I2. On encountering B, S gives B dot C. Name this as I3. And on D, I go to D dot. We will call this I4. Now remember, this is a final state and also this is a final state, because I can't do any other step on these two set of items. And also I did not include the productions of A because I didn't have any. Now taking an A move from I2 will take me to S gives B A dot C. Let's call this I5. While a C move from I3 will take me to S gives B C dot. Let's call this I6. And also this is complete. Now a simple move of C from I5 will take me to B A C dot. Let's call this I7. And hence we are done with building the automata, and this also is the final state. Now we will see how to build the parsing table for LR0 grammars. We have two parts of the table called action part and go to part. The action part contains about the transition, and the go to parts to what state I go to. Now I0 on capital S takes me to I1, so I'll write down 1 here. and I0 on capital B takes me to I3, so I'll write down 3 here, and capital 0 on B takes me to I2, so I'll write this as transition S2, as in shift 2. And also now 0 on small d takes me to I4, so I'll write it down as S4. Now I1 is the final state, so, and it also contains the complement grammar, which completes my original grammar. So I can put an accepting sign in the dollar symbol. Now considering S2, I2 on capital A takes me to I5, so I can put 5 here in the table, and I3 on small c takes me to I5, I7, sorry, I6, so S6. Let's leave the final state for a while now. Let's consider I5. I5 on C takes me to I7, so I'll write down S7 here. Okay, now this is the part where the difference between LR0 and SLR1 comes. Final states. The first one is S gives D dot. The production number is 3. So the on 4, whenever I encounter any non-terminal, I will reduce the non-terminal. So R3 in LR0 parser. And similarly for sixth one, 6 is complete. So which is R2. So I'll write down 2 here. And for I7, this is 1. So I'll write down 1 everywhere in case of non-terminals. Oh, terminals, I'm sorry. SLR1. In SLR1, we have access to the next symbol, as in 1 look ahead. The 1 denotes that. So we will calculate follow of each non-terminal and see when we have to make a reduction move. Finding follow of each non-terminal. Follow of S would be the start symbol, so S is start symbol, so dollar, and follow of A would be C, and same for B. Considering S gives D dot in the fourth move, so whenever I see a final move, I'll consider the LHS and find the reduction for it. S gives dot D. I'll find the follow of S, that is dollar, and I'll place the reduction move in the dollar column, which is here. So I'll write here R3. And now for sixth element, which is S gives BC dot. Now the reduction takes place, and again on encountering I6, S gives BC dot, which is the second reduction. So I need to write R2 in the follow of S, which is dollar. So R2 here. And similarly for BAC, the follower would be dollar only. So I'll write down R1 here. And that completes our SLR1 table, both LR0 and SLR1. Consider a string like alpha, D, beta, and our grammar remains the same. S gives B, A, C, S gives B, C, and S gives D. Now what LR0 does is, when I look at beta in my input buffer, it reduces D to S, which will later produce error since D can be only last symbol of the string to be a part of the grammar. Such moves are prevented by SLR1. So LR0 is same as SLR1, except it doesn't give error early like SLR1, but both parse to similar results, and therefore LR0 is equal to SLR1.